Today, we are diving deep into one of the most incredible, high-tech factories in the entire universe, a single living cell. We're going to peek inside and figure out how these microscopic powerhouses manage their workforce, their enzymes, with a kind of precision that is just mind-blowing. So let's start with a question. What could a bustling, noisy factory possibly have in common with a tiny, silent cell? Well, believe it or not, the answer is management. Both are just humming with activity, right? Turning raw materials into crucial products. In a factory, if the management is bad, you get chaos, you get waste. But in a cell? Oh, it's literally the difference between life and death.
And that takes us right into the cell's control room. Just like a factory floor manager has to watch every single production line, the cell is juggling thousands of chemical reactions all at the same time. If it didn't have a solid control system, it would just burn through energy and resources, making all sorts of stuff it doesn't even need.
And the stakes here are incredibly high. We're talking about coordinating all those metabolic processes, saving every bit of precious energy, and being able to react on a dime to changes in the environment. And maybe most importantly, it has to know when to stop producing something it already has plenty of. It's this constant, relentless balancing act. So how does it pull this off? Well, the cell basically has two genius strategies for managing its enzyme workers. First, it can control the size of its workforce, deciding just how many enzymes it needs on the clock at any given moment. And second, it can control the speed of the workers it already has, basically telling them to work faster or maybe take a coffee break. So let's look at that first strategy, hiring on demand. This is all about controlling the amount, the concentration of any given enzyme. You can think of it like one of those super efficient factories that doesn't keep a huge warehouse full of parts. Nope, it makes enzymes only when they are absolutely needed, just in time. So in this cellular factory, you've got two kinds of employees. First, you have your constitutive enzymes. These are your permanent full-time staff. They're always there, always on, taking care of the essential day-to-day housekeeping, things like breaking down sugar for energy. But then you have your inducible enzymes. These are the freelance specialists, the temporary hires. They only get called in when a very specific job comes up. And this, of course, saves an absolutely massive amount of energy. And this chart shows that difference so clearly. Just look at the orange bars on the left. That's our inducible enzyme. See how its activity starts out super low, but then bam, the signal arrives and its production just skyrockets. Meanwhile, the constitutive enzyme on the right just keeps chugging along at that same steady pace, always ready for its routine job. So how does this on-demand hiring actually work on the genetic level? Well, a classic example is an E. coli bacteria. See, when there's no lactose, no milk sugar for it to digest, this little thing called a repressor protein acts like a physical roadblock. It sits right on the DNA and blocks the cell's machinery from reading the gene. No gene reading means no enzymes are made. The factory is officially closed. But the second that lactose shows up, everything changes. The lactose molecule itself comes in, grabs that repressor protein, and just yanks it off the DNA. And just like that, the road is clear. The cell's machinery can zoom in, read the gene, and start cranking out the exact enzymes needed to break down that lactose. The factory roars to life, but only when it's needed. It's so efficient. And this isn't just some weird thing that bacteria do. This is happening inside of you right now. A perfect example is the enzyme lactase, the one we use to digest milk. For many people, it's inducible. Another great one is CYP2E1, an enzyme in your liver that helps break down alcohol. Its levels actually go up with chronic drinking. It's part of how people develop a tolerance. Your body is literally hiring more workers to handle the job. All right, so that's strategy one. Now let's move on to the cell's second big trick, flipping the work switch. This isn't about hiring and firing. This is about managing the enzymes that are already there on the factory floor and just telling them how fast to work. And the logic here is pretty simple, right? Sometimes you don't need a whole new team. You just need your current team to speed up or maybe hit the brakes. A signal comes in, and instantly the entire production line can accelerate or grind to a halt. This is a much faster way to respond than building brand new enzymes from the ground up. And the signals the cell uses to send these instructions, they're called modulators. These are just small molecules that bind to an enzyme and act like a gas pedal or a brake pedal. Some are activators. They tell the enzyme to go, go, go. And others are inhibitors. They tell it to slow down or just stop completely. And the most elegant, the most sophisticated way this happens is through a system that's basically a remote control for the enzyme. It's called allosteric regulation, and it allows for this incredibly precise, fine-tuned control over what an enzyme is doing. And the name itself actually gives away the secret. Allosteric comes from Greek, and it literally means other shape. And that's the key. The regulation doesn't happen at the enzyme's main workspace, the active site. It happens at a totally different spot, an other site. Okay, so let's look at how this works, because it's brilliant. On the left, we've got activation. A modulator clicks into that special remote control site. That click causes the enzyme to change its entire 3D shape. And that change makes the main active site a perfect fit for its target. Now, on the right, we see the opposite. A different modulator binds to the remote control site and it warps the active site, making it useless. It's such a simple, indirect, but powerful mechanism. The cell uses this for what I think is the ultimate efficiency hack. It's called feedback inhibition. Imagine a long assembly line with multiple steps. When enough of the final product has been made, that very same product travels all the way back to the first worker in the line and tells it to stop. And this is pure genius. Why? Because it shuts down the entire production line right at the source. There's no point in stopping an assembly line halfway through. You stop it before it even starts. That's how you save the most energy. Now, here's a really fascinating thing about these allosteric enzymes. They have this very distinctive S-shaped activity curve. It's not a smooth, steady rise. Instead, they kind of have a slow start, but then once they get going, they rapidly accelerate. This signals something called cooperativity. It's like the first molecule binding makes it way easier for the next one to bind. And the next one. It's like a turbo boost, suddenly kicking in. Now, this whole idea of cooperativity, where the different parts of an enzyme seem to work together, well, it brings up a really interesting scientific debate. When these big, multi-part enzymes change their shape, does the whole team switch over at once, or is it more like a domino effect? And this leads us to two main theories. At the top here, you have the concerted model. This idea suggests that the entire enzyme complex just flips from one state to another all at once. It's an all-or-nothing team switch. But the sequential model, on the bottom, suggests it's a chain reaction. One part changes first, which encourages its neighbor to change, which then affects the next one, and so on down the line. So just to recap, the concerted model is like flipping a single switch for the whole team, all at once. The sequential model is more like a domino rally, where the change happens one piece at a time. The real truth is probably pretty complex. Different enzymes seem to use different strategies, or maybe even a mix of both. It's something scientists are still actively figuring out. So when you just step back and look at the whole picture, it's incredible. From making careful hiring plans by controlling which genes are turned on, to using these unbelievably sophisticated remote controls to manage the workers already on the floor, the cell is just an absolute master of management and efficiency. And it really makes you wonder, doesn't it? We've just barely scratched the surface of one tiny piece of how a cell stays in control. So the question I want to leave you with is this. If this is the level of complex, perfect management happening in just one single biochemical pathway, what other invisible, perfectly run factories are humming away inside of you right this very second?